For decades, sports science has relied on the stretch-shortening cycle to explain the explosive power of human jumping. The theory suggests that as an athlete drops into a jump, their tendons stretch to store energy, which then passively recoils to launch them into the air. This chart shows the mechanical difference between two specific movements: a squat jump, starting from a static pause, and a counter-movement jump, which uses a rapid downward dip before takeoff. Baseline experimental data from Bobbert, Karakawa, and Fukushiro shows that the counter-movement jump consistently yields a height advantage of between 3.4 and 5.0 centimeters. Lifting a 70-kilogram human that extra 5 centimeters against gravity requires a specific amount of mechanical work. The physics are absolute. It takes up to 34 joules of additional energy to achieve that height gap. Under the stretch-shortening theory, that extra 34 joules must come entirely from elastic recoil, specifically from structures like the medial gastrocnemius, or MG, tendon in the calf. Direct in vivo measurements by Fukushiro quantified exactly how much elastic energy is stored in this tendon during these jumps. This graph compares the required energy against the available energy. The measured difference in stored tendon energy between the two jump types is exactly 3.4 joules. The human body produces an extra 34 joules of work using a mechanism that can only physically supply a tenth of that amount. Even if the MG tendon accounts for only half of the total elastic contribution in the lower leg, doubling that figure yields less than 7 joules. The system is operating with a 27 joule deficit. The numbers do not balance. The classical framework of the leg acting as a passive spring fails a basic quantitative energy budget, rendering the accepted model of human propulsion mathematically impossible. The energy deficit is only the first physical contradiction. The classical model also breaks down when we examine the biological speed limits of fast-twitch muscle fibers. In 1938, physiologist A.V. Hill established a foundational law of exercise mechanics, the force-velocity relationship. This chart displays Hill's equation. The y-axis represents force, and the x-axis represents contraction velocity. The curve illustrates a strict constraint. As a skeletal muscle shortening velocity increases, its capacity to generate force drops drastically. In the terminal phase of a vertical jump, the athlete's upward limb velocity reaches its absolute maximum. According to Hill's law, a muscle contracting at this extreme speed produces almost zero force. In vivo ultrasonic measurements confirm that muscle fibers shorten rapidly during this exact liftoff window. Under classical mechanics, this high-speed contraction negates the high force production required to leave the ground. Furthermore, at the high frequencies of a rapid counter-movement jump, the viscous damping of muscle tissue absorbs a significant portion of the stored elastic energy. Internal friction drops the net efficiency of a purely elastic system below 40. By constant volume constraint, longitudinal shortening causes proportional radial expansion. The inextensible deep fascia fiercely resists this, forming the intramuscular pressure, or TIP, model. Pressure equals length change divided by volume times K, the fascia's radial stiffness. Because the fluid cannot escape, this internal radial pressure acts perpendicular to the fiber direction. It creates a hydraulic wedge effect, driving massive outward force against the surrounding musculoskeletal levers. This pressurized fluid medium acts as a variable ratio transmission. It maintains high torque at the joint, bypassing the velocity limits of Hill's equation, because the force is driven by volume redistribution rather than fiber shortening. The muscle belly functions as a high-power hydraulic engine, generating force through internal pressure that far exceeds the linear pull of individual fibers. We can verify this fluid dynamic behavior by mapping the TIP model against temporal electromyography, or EMG data, which records the exact millisecond electrical activity of muscles during a jump. This timeline tracks the liftoff sequence. Our critical reference point is T0, the exact moment of maximum counter-movement depth, immediately before upward liftoff begins. First, passive pressurization. Forefoot weight shift geometrically deforms the calf, passively stretching the Achilles to generate initial fluid pressure. Anomalously, EMG shows the tibialis anterior activating 250 milliseconds early. It provides no propulsion, instead establishing a structural rail for pressure buildup. At T0, active amplification begins. Major muscles synchronize to trap fluid within the leg. The triceps suri fire in a near isometric state. Fibers lock their length, creating high tension with near-zero shortening velocity, actively amplifying compartment pressure. Explosive jumping relies on fast twitch fibers locking isometrically, converting the lower leg into a sealed, high-pressure chamber. Because the deep fascia prevents the compartment from expanding radially, the resulting hydrostatic pressure must find an escape route. The pressure propagates proximally. It travels upward through the posterior compartments of the leg, applying direct vertical force to the bottom of the femur and physically pushing the thigh bone upward from below. If hydraulic push-up drives the jump, inverse dynamics must show power originating at the ankle. During early liftoff, knee power flatlines or turns negative, while the ankle joint dominates positive power output, generating 50 to 70% of net propulsive force. In this model, extensor muscles like the quadriceps do not drive the jump. They co-contract to maintain skeletal orientation and compartment integrity under massive internal pressure. Knee extension occurs as a mechanical consequence of hydraulic pressure escaping proximally from the ankle, driving the femur upward. If the tip model represents universal structural physics, it can be mathematically simulated and scaled into functional engineering. The current standard for artificial soft robotics is the McKibben pneumatic muscle. However, these are tethered systems, requiring external air compressors for actuation. Applying the biological pressure model creates a self-pressurizing hydrostatic actuator, mimicking the multi-layered architecture of human deep fascia. Replicating this effect requires specific helical angles, an outer layer at 60 degrees, an intermediate layer at 45 degrees, and an inner layer at 30 degrees. Applying axial tension to the ends of this specific helical shell forces a passive geometric compression of the fluid trapped inside the cylinder. The engineered geometry generates internal hydrostatic pressure through tension alone, eliminating the need for an external pressure source. The deep fascia functions as a highly optimized composite structure, specifically designed for fluid dynamic pressure containment. Computational comparisons between the biomimetic actuator and the traditional McKibben muscle reveal the exact mechanism behind the human body's missing energy. Traditional McKibben pneumatic muscles reach their operational limit at 0.6 megapascals of internal pressure. The biomimetic actuator outputs 32.0 megapascals of internally generated pressure, a 53-fold increase over the pneumatic design. This pressure multiplier allows for a theoretical power-to-weight ratio of 242 kilonewtons per kilogram, creating an immense density of deliverable force. The 250 joules of missing energy identified in Act 1 exist within the pressure field of the muscular compartments themselves. The mathematical deficit of the stretch-shortening cycle disappears once we stop measuring the leg as a linear spring and start measuring it as a self-pressurizing hydraulic amplifier.